F on 1. And if we wish, we can put it on this picture down here too. We also could have gotten our direction from the right-hand rule. V crossed with B would give down from negative j hat. So we see here this is a little bit similar to the work we did on two current carrying wires. We found when two wires carried current in the same direction they were attractive. Here we have two positive charges moving in the same direction. They experience an attractive force. That's not a surprising result because moving charge is what current is. Alright, so there's an expression with symbols. Since we're asked for the force, why don't we go ahead and calculate that value? So we do know all of our numbers. Minus 4 pi times 10 to the minus 7 Tesla meters over amps times E squared 1.60 times 10 to the minus 19 coulombs squared. V squared is 0.1 times 3 times 10 to the 8 meters per second. Can't forget to square that. Divide that by 4 times pi. Our R was 10 nanometers. 10 times 10 to the minus 9 meters squared, j hat. So we get the magnetic force on charge 1 is equal to minus 2.30 times 10 to the minus 14 newtons, j hat. So there's our magnetic force on charge 1 due to the motion of charge 2 and the motion of charge 1. So charge 2 moves, makes a magnetic field. Charge 1 is a moving charge in a magnetic field. It feels a force. Now we're not finished. A asks for the magnetic force of each proton on the other. We've just found the magnetic force on charge 1. What about the magnetic force on charge 2? Two strategies for solving this problem. You can either go through the entire process again. You can find the magnetic field made by charge 1, and then you can find the magnetic force on charge 2, or you can think about Newton's third law. Newton's third law says for every force there's an equal and opposite force. So the magnetic force on charge 2 due to charge 1 is the negative of the magnetic force on charge 1 due to charge 2. That would mean that force would be plus 2.30 times 10 to the minus 14 newtons, j hat. That's the faster way to solve this problem. If you did it the long way, that certainly would not be incorrect, but it might use up a bunch of your time. Okay, part B. Find the electric field around each charge. So these are plates. They make an electric field. Because that charge is in an electric field, it feels an electric force. The other thing we know is that the charges are going straight through. It tells us that the net force on each proton has to be 0. So let's work with that idea. So in part B, each of our protons go straight through. So there's charge 1. I'll just put a little arrow here to remind us that it goes straight through. Why don't I draw a free body diagram and apply my Newton's second law, because I know it goes straight. So if I think about what the forces acting on my proton are, I've already established that it has a magnetic force that points down. So there's my FB, and I found that in previous. Another thing I have is I have two positive charges close together. They feel a repulsion due to Coulomb's law. So there's going to be a repulsion between them. There are different things you could call that. You could call it FC for Coulomb's law. You could call it F12 for the force of on 1 by 2. Different things to call it. I'll go F12. And now there must also be an electric force because it's in an electric field. Right off the bat, I don't know which way that electric force points. I'm just going to pick down. So there's my free body diagram. This is for charge 1. Next, I'll write my Newton's second law. Sum of the forces acting on charge 1 is equal to the mass of charge 1 times its acceleration, but I know that acceleration is going to be 0. So the electric force between them plus the magnetic force between them plus the force due to the electric field between them, they all have to sum to 0. So my force between them, F12, why don't I find that off on the side? So F12 We'll use Coulomb's law, K times Q1 times Q2 divided by the distance between them squared, 8.99, times 10 to the 9 newtons meters squared over coulombs squared, times Q1, which is 1.6 times 10 to the minus 19 coulombs, times Q2, which is the same, divided by R squared, that was 10 nanometers. So the magnitude of the Coulomb force between them is 2.30 times 10 to the minus 12 newtons. Okay, in my picture that points straight up, so I've got plus 2.30 times 10 to the minus 12 newtons J hat. My magnetic force, I found that a moment ago, that was minus 2.30 times 10 to the minus 14 newtons J hat. And for my electric force, I remember that electric force is equal to charge times electric field. My charge is my proton charge times my electric field. Remember, I said I didn't know which way the electric force pointed, the electric field pointed. This equation is going to take care of that for me because I've been very careful with all of my vector notation. So to solve for my electric field then, E is equal to 2.30 times 10 to the minus 14 newtons J hat, subtract 2.30 times 10 to the minus 12 newtons J hat, divided by the charge on a proton, gives me an electric field that charge 1 is sitting in of minus 1.42 times 10 to the 7 newtons per coulomb J hat. The electric field does turn out to be pointing down, so my initial guess of the electric force pointing down was a good one. That turned out to be correct. To find my electric field, which charge 2 is sitting in, I'll do the same thing again, but I'll apply it to charge 2. We can reuse a lot of what we've done here. So on charge 2, that's a positive charge. I know that my magnetic force points up. This time I'm going to guess that my electric force, due to it sitting in an electric field, points up. Charge 2 is repelled by charge 1, so that Coulomb force between them is going to point down. I know that the net force is equal to mass 2 times its acceleration. That's going to be 0. So I've got my electric force, which is E times E, plus my magnetic force, which is plus 2.30 times 10 to the minus 14 newtons J hat, plus my Coulomb force, which points down, so that's minus 2.30 times 10 to the minus 12 newtons J hat, all mass times acceleration. Solve for E, and for this electric field we get positive 1.42 times 10 to the 7 newtons per coulomb J hat. This problem is a little bit different than anything we did in the lectures, but it's certainly built from everything we did in the lectures, so this would be fair game for our final exam as well.